Hey everyone, welcome to this explainer. Today, we're jumping straight into something that is an absolute game changer for local artificial intelligence, Google's Gemma 412b unified model. We're going to look right under the hood at its architecture and, more importantly, figure out exactly how you can run a true frontier-class multimodal AI right on your everyday machine.
So let's start with the big question: what does it actually take to run a frontier multimodal AI locally? I mean, if you've been following the AI space, you probably assume it requires, massive, insanely expensive server clusters, pricey cloud subscriptions, and honestly, a whole lot of patience for latency. Historically, getting a model to seamlessly ingest text, images, and audio all at once, that's been a massive headache reserved for big data centers.
Well, prepare to have those expectations totally shattered. 16. That is the magic number today. Google's Gemma 412b unified model delivers state-of-the-art multimodal reasoning, and it runs smoothly on a standard consumer laptop with just 16 gigabytes of RAM. Yep, we're talking about fully private, offline intelligence running right there on your everyday hardware.
Okay, here's our roadmap for today. 1. The Local AI Bottleneck. 2. The Encoder-Free Architecture. 3. Processing text, images, and audio. 4. Running on your laptop. And 5. Mastering thinking mode. Let's get into it.
Starting off with Section 1, the Local AI Bottleneck.
Traditionally, multimodal AI models have this huge flaw. They need massive, dedicated translators for every single data type they encounter. If you wanted a model to see, you had to bolt on a separate frozen vision encoder, and that alone costs anywhere from 150 to 550 million parameters in memory overhead. Wanted to hear? Add on another 300 million parameter audio conformer. It's basically like a heavy toll booth for your data. Processing stuff through all these separate encoders fragments your memory footprint and introduces a ton of latency, which literally drains the precious resources right out of your local machine.
Which brings us to Section 2, the Encoder-Free Architecture.
The contrast between the old way and this new way is kind of mind-blowing. The bloated traditional models rely on those heavy 150 million plus vision and 300 million plus audio encoders we just talked about, but Google's 12b unified model, they completely eliminated this separate audio encoder. Just skip those 12 conformer layers entirely. And for vision, they replaced 27 massive vision transformer layers with one tiny 35 million parameter embedder. It's an absolute masterclass in optimization.
The documentation actually puts this perfectly. It says, bypassing heavy multi-stage vision and audio encoders entirely, multimodal data is fed straight into the LLM backbone, reducing multimodal latency. Basically, because the model natively speaks all these modalities directly into a single decoder-only transformer, all that lag and memory overhead just vanishes. It's like a unified sensory interface built straight into the core language model itself. Let's look at Section 3, processing text, images, and audio.
So how does this pipeline actually work in practice? Well, step 1, the model takes raw 48 by 48 pixel patches for vision and raw 16 kilohertz audio signals that are sliced into 40 millisecond frames. Step 2, and this is the cool part, instead of running those through deep, complex neural network encoders, it uses a lightweight linear projection. We're literally talking about a single matrix multiplication here. Then, step 3, that projected data is dropped directly into the LLM's embedding space. The raw visual and auditory data goes straight into the brain, interleaved right alongside your text prompts without missing a beat.
And for developers out there, this streamlined pipeline creates an incredible advantage: unified fine-tuning. In the old paradigm, teaching a model a new visual skill meant you had to code-tune those frozen encoders alongside the text model, which is a total engineering headache. But with Gemma 412b, vision, audio, and text all share the exact same weights inside the unified transformer. That means you can use a downstream adapter, like LoRa, and update the entire multimodal token loop in a single pass. It is so much more efficient.
Moving right along to Section 4, running on your laptop.
Okay, if you want to run this locally, quantization is going to be your absolute best friend. It's essentially just compressing the model's weights to save space. Look at the 4-bit quantization level. Developers can run this entire 12 billion parameter powerhouse in just 7 to 8 gigabytes of total memory. If you want a little more precision, 8-bit fits perfectly into 13 to 14 gigabytes. That makes it an absolute breeze to run on a standard 16 gig Mac or a PC with a consumer NVIDIA GPU.
But hey, it's not just about fitting it into memory, right? It's about speed. Google equipped this model with multi-token prediction, or MTP, drafters.
So instead of guessing just one word at a time, the model predicts several tokens ahead simultaneously. This supercharges your inference speed and gives you near real-time responsiveness. That is absolutely critical for autonomous agentic workflows or voice apps where you really can't afford any delay. Plus, your data stays 100% on device for total privacy, and the whole thing is available under a highly permissive Apache 2.0 license.
Finally, Section 5, Mastering Thinking Mode.
Now, Gemma 4 models are designed as highly capable reasoners, but you've got to know how to drive them. To vastly improve the model's accuracy, you need to use a specific control token, the think token, which is wrapped in angle brackets and pipes. By placing this token at the very start of your system prompt, and remember, Gemma 4 relies on standard system, assistant, and user roles, you manually trigger the model's step-by-step internal reasoning mode.
When you enable this thinking mode, the model actually changes how it responds. It generates a thought channel tag, writes out its internal reasoning process, and then closes that channel. It literally shows its work step by step before it gives you the final answer. Doing this significantly boosts its performance on tricky stuff like complex math, coding, or multi-step agentic planning.
But listen up, because there is a critical best practice here for developers: the multi-turn chat rule. You must only keep the final visible answer in your chat history. You have to strip out those thought blocks before you pass the conversation history back to the model for the next turn. If you feed its prior thoughts back into the prompt, you're going to risk confusing the model and degrading its context window. You basically have to let it think fresh every single time.
So there you have it. We've seen how Google ditched those heavy legacy encoders to create a sleek, latency-free, multimodal model that fits effortlessly into just 16 gigabytes of RAM. You've got the blueprint to run it, fine-tune it in a single pass, and unlock its deepest reasoning capabilities. So I'll leave you with this question. With a fully private, highly capable multimodal reasoning engine sitting right there on your laptop, what agentic workflow are you going to build first? Get out there, start experimenting, and have some fun with it. Thanks for tuning into this explainer.